Hi, this is Tom Sargent. I'm pleased to be assigned the task of discussing the paper by Martin Ellison and Andrew Scott, Managing the UK National Debt from 1887 to 2016. This is an impressive data gathering and data creation enterprise. So the idea of the paper is they're going to use bond, called or otherwise known as gilt prices, plus prospective coupon streams and par values for each bond to deduce Hicks arrow prices and associated zero yield curves for dates from 1887 up to the present. That itself is an ambitious data gathering task. Then they're going to use those prices together with data on the promised coupons and the principal payments, which they know from the details of the bond, to do, quote, government budget constraint arithmetic, and to do it correctly. They have both marketable debt, which are these gilts. There's 522 of them. And they have non-marketable debt. And they say interesting things about both of these. The non-marketable debt includes debt from the UK government to the US government incurred during the two world wars. So the theory that they use, two pieces of theory basically: Arrow-Hicks prices, first class theory, and a properly written down government budget constraint. So let's look at the theory of asset pricing that they use, which is going to guide the way they look at the data. Let's just take a continuation payout stream, which I'm going to call OT. And for them, this is going to be a particular. This is going to be the payouts in a particular. So here we are with a particular bond. We have a payoff stream. The superscript denotes the now, and the subscripts denote prospective payoffs. So I'm calling that a continuation payoff stream. And for each bond, OT is observed. They can read it from the contract. And what they also observe is the price of that bond at date T. And that bond, their theory, this is a key theory, that price is the inner product, that's sum. That should go, by the way, to T. That should go to capital T right here. It goes from from tomorrow onto the horizon of the bond. They have some interesting bonds because some of their horizons are infinite, and they handle that in a constructive and reasonable way by having ex post horizons. I recommend that part. So these PT, that's the price today of $1 or a pound T plus J periods from now. And they have the units of pounds at T to pounds at T plus J. So these are the two observed things. And then the key thing is, and this is the insight they use, with enough bonds and prices, with enough continuation payoffs and enough prices at each date, they can back out these Hicks arrow prices. And those are the fundamental things that their analysis works with. The Hicks arrow prices are related to what are known as yields or yields to maturity by this formula, which implies that the yield, the zero coupon yield on a J period zero coupon bond is related to the Arrow-Hicks price by this formula, and they're going to report those yields. And the so-called yield curve is just going to put that sequence on the table for every T. They also talk about something called returns. And what a return is, it's just this. It's a return on a zero coupon J period security, and that's what you get next period, the numerator, for what you paid for at this period. That's just the gross return. And the net return is this piece, 1 minus the okay, so that's called the 1 period return, and they present some really interesting graphs of both yields and returns and how returns vary with J. And they do some really interesting counterfactual experiments, freezing their conceptual experiment is they freeze at each date the vector of Hicks arrow prices, and then they study the consequences of alternative debt management strategies. So to talk about, shed light or tell you what my reading of their paper made me think about, I'm going to set the stage with Barrow 1979. And Barrow's budget constraint was a very, very special case of what Ellison and Scott work with. So here it is. ST minus 1T is 1 period debt. Barrow just worked with 1 period risk-free debt. So in our notation, G is government expenditures, T is total tax collections. This is the debt that's due. That's the debt that's going to be due next period. You issue it, and you get these risk-free Hicks price multiplying what you promise. What Barrow assumed, you'll recall, is this for all T. So he assumed Barrow's model is virtually isomorphic to Hall's model of permanent income. So both Hall and Barrow assumed assumption like this. And Barrow's model was that the government chooses jointly a sequence for taxes and risk-free debt issues to maximize this discounted quadratic, the expectation of this discounted quadratic in total tax collections. So this is Barrow's budget constraint. Let's get Ellison and Scott's extension. They're going to write it like this because they have many more maturities. So last period, at time period T, the government had issued bonds whose coupons and principals gave rise to sequences of promises, this particular sequence of promise. Today's arrow Hicks price of that vector of that sequence is that. Take price times quantity, that's the value of what I owe this period. I have to add this because PTT is 1. So this is what I owe on my debt this period. This is the additional amount government expenditure. That's my deficit. And the value of debt that I issue today is going to have to equal that. That's a government budget constraint. We're abstracting from seniorage, which would be important to add for certain countries in certain periods. So STT plus J that's the sum of coupon payments that you promised and principal payments that you promised. So I'm going to, in the interest of, so they do, Ellison and Scott do some very creative and instructive things with this equation. And they rewrite it in certain ways and get some very interesting decompositions actually get time series decompositions of this object, and they tell you what contributed to growth or decline in that. I'm going to go a little different direction, partly because they got me thinking about Barrow and other things. I'm going to rewrite. I'm just going to rearrange terms. I'm going to rewrite that budget constraint like this. That's just algebra. And what this turns out, this is what it turns out to be. So I come into a period and I have some one period debt that came due. That's what I owe. That's my government deficit. And so, like, how do I finance that? And this first term is, I issue some of the longest term stuff. That's what I pick up. And then here, I do a lot of shuffling and rescheduling because I came in owing this vector, and I'm going to go out owing this vector. So their equation allows rescheduling, refinancing, repurchasing, and reissuing. And I've just written this to highlight this. So now it's very easy to take Barrow's model and write a linear quadratic dynamic programming problem that kicks out the optimal tax and debt policy. Well, if you use this equation and stare at it, you can make some progress in doing that. Now, Ellison and Scott actually don't. This paper is not designed. This paper does not focus on an optimal debt problem, although it's set up to go the next step. So here's this finding of states in art. So I'm going to take this equation and see what we can get. Xt is going to be a piece of the state at t, and ut is going to be a vector of controls. So if you think about that equation, what xt is going to be, the state is this vector. Look at this vector. That's the whole vector of things that promises that you've made last period that you're going to have to honor in the future. That's what you have to pay today, and these are continuation. UT is, well, you can rescale and reschedule everything subject to that constraint. So that's your control. And here's your law of motion. Tomorrow's state is just UT. So you've got a lot of control of tomorrow, that piece of the state. The other part of the state is, well, like in their formulation, government expenditures and taxes, they're going to take that as part of the state. And I'm going to think about that as driven just by, let's say that we could think of that driven by a standard linear Gaussian time series model. And now I'm going to think of, they take these PT t plus 1, actually tt plus j, they take that vector as given every period, as exogenous. Well, I'm going to do a version of that. I'm going to assume it's governed by a finite state Markov chain. So those arrow securities prices, they jump around with dynamics. I'm going to describe that by a finite state Markov chain. So let's see why that's going to be. So I'm going to govern this. So we're assuming that PTT plus J is governed by a finite state Markov chain. The virtue of that is, if we now stare at this budget constraint, and then this little equation, you could see where the elements of the state and control. If you stare at this equation, and solve for TT as a function of everything else on the right-hand side. Well, if we return to Barrow, the Barrow philosophy, TT squared now, it's a quadratic function of the states and controls. And I should add CT. It's a quadratic function of all those things with time-varying coefficients that are determined by this Markov chain. So when PTT plus J is a finite state Markov chain, this problem, Barrow's problem, maximizing this, it now just becomes a linear quadratic Markov jump, so-called Markov jump dynamic programming problem. And that's really easy to solve. And what that would allow us to do is use the more sophisticated arithmetic that Ellison and Scott have done with we don't have to assume constant interest rates. If we can model those as moving around with, if we could model their data as moving around with a finite state Markov chain, we can make a lot of progress. And then, the reason I go off in this digression, Ellison and Scott's 3 debt management exercises use part of the above model, but more could be done. So I'll just conclude by saying well, why stop here? Why stop with this objective? Barrow laid down an objective. You could think of a lot of subsequent work as asking, well, that objective is an approximation to something that comes from a more fully articulated model in which there's a Ramsey problem, perhaps, and there's either a representative or a set of heterogeneous agents, and the Ramsey plan is solving a Pareto problem. And there's some work on that by Bandari, Golosov, and others, and they get some striking results about asymptotic levels of government debt and rates of convergence and various other statistics about what the government portfolio looks like. And Scott and Ellison and Scott have given us the material for the data for actually understanding and interpreting British history, fiscal history, in light of theories like this. So I feel lucky to have been asked to discuss this paper. It's ambitious. It's an ambitious data collection and pattern recognition exercise, and it's guided by a first-class theory, which is the one of Aaron Hicks. So thank you.